To sum up, the air interface is the key to end-to-end bandwidth. A set of solutions can be used to increase the air interface bandwidth, such as adjusting the signal level and controlling the quantity of subscriber allocated with numbers, higher priority QoS-based scheduling, resource reservation, super uplink, and new slot configuration. Now, let's go to see the second basic service capability, end-to-end latency and reliability. URLLC was introduced in 3GPP Release 15 and enhanced in 3GPP Release 16. 3GPP Release 15 have been frozen in 2019 Q1 and 3GPP Release 16 in July 2020. 3GPP Release 15 defines the basic URLLC functions. Technologies involved in 3GPP Release 15 have met the requirements for commercial use of some applications. 3GPP Release 16 further improves the reliability and capacity while ensuring shorter latency. In this part, let's take a look at how to ensure end-to-end latency and how to improve reliability. With the development of 5G, the 5G 2B industry has higher requirements on low latency and high reliability on the basis of high bandwidth. URLLC also promotes the development of vertical industries. It implements 1 millisecond latency and a 99.999% reliability on the RAN side. There are different requirements on latency in different industries and applications. For example, autonomous driving, VR/AR, smart grid, smart manufacturing, healthcare, smart city, UAV, and etc. In different scenarios, there are different applications. There are also latency and reliability requirements for specific applications. Let's have a look at what solutions can be used to ensure latency and reliability. The first solution aims at latency assurance. The end-to-end latency needs to be analyzed in terms of architecture, air interface, device, and service. Devices, including microwave devices, routers, and core network devices, are relatively mature with low latency achieved. At the service level, we do not need to lay much concern on latency. So how to reduce latency in terms of architecture and air interface will become our focus. As for architecture optimization, the MEC solution is proposed. The user plane can be moved. The user plane can be moved downwards by deploying MEC to reduce the transmission latency. In the traditional architecture, data needs to be sent to the core data center, DC, for any services. If a service request is sent, the terminal sends the request to the server in the core DC. The server responds, and the terminal then performs the corresponding action. In this way, high latency is introduced. To support services with low latency requirements, moving the core network downwards is proposed. Different services have different requirements on the architecture. In the following, we will take a look at the architecture required for HD video services, services with massive low-rate connections, and autonomous driving services. Generally, video services are deployed in the regional DCs because such services do not have high requirements on the latency, and the CDN is also deployed. With video services deployed in regional DCs, network congestion caused when all video data is sent to the core server can be prevented, while latency is ensured. With video service deployed in regional DCs, network congestion caused when all video data is sent to the core server can be prevented while latency is ensured. The CDN relieves the network congestion and accelerates the response to website access requests. and accelerates response to website access requests. Services with massive low-rate connections, such as water meters, electricity meters, and gas meters, are generally deployed on the core network side because such services do not have high requirements on latency. Autonomous driving has high requirements on latency. As such, the user plane can be moved downwards by deploying the UPF in the HDC. This significantly reduces the transmission latency and ensures experience in autonomous driving service. Besides architecture optimization, many efforts have been made on the air interface to ensure transmission latency. Now, let's take a look. In 4G, a fixed subcarrier spacing (SCS) of 15 kHz is adopted. In 5G, numerology is introduced to support different SCSs for services with various latency requirements. In this way, scheduling time is reduced. A larger SCS results in a shorter slot and a lower latency. In addition, the mini-slot feature can be used to reduce the RTT. In terms of latency, architecture optimization and air interface solutions can be used. As for reliability, the active standby mode is supported. From this slide, we can see that all devices and gateways work in active and standby mode. Such devices and gateways include CPE, G-Node Bs, CSG on the base station side, Service Gateway ASG, and MASG on the aggregation side. The entire network is in active and standby ring backup mode. To be honest, this active standby mode is the most direct and effective solution to ensure reliability. In addition to the active and standby mode, 3GPP defines 3 solutions for improving link reliability. These solutions include redundant transmission with end-to-end paths, redundant transmission with dual N3 tunnels, and redundant transmission over the air interface with multi-RLC links. Solution 1 designs redundancy for end-to-end paths between devices. Solution 2 designs redundancy for N3 tunnels between the RAN side and the core network. Solution 3 designs redundancy for RLC links over the air interface on the RAN side. With these solutions, end-to-end reliability can be improved through transmission redundancy at different levels. Here, I'd like to talk about 2 solutions used to guarantee air interface reliability: interference coordination in the beam domain and interference coordination in the time and frequency domains. First, let's see how interference coordination in the beam domain works. Assume UE1 is located at the cell edge. It will suffer interference from the beam of UE2. In this case, CBF can be enabled to reduce interference. CBF coordinates the beam directions of the UE in intrafrequency neighboring cells, so that the beam direction of the UEs at or near the cell center are changed to avoid causing interference to CEUs in the neighboring cells, thereby improving spectrum efficiency of CEUs. In this example, the beam direction of UE2 is changed to avoid interference to UE1. When 2 UEs are close to each other, the solution of interference coordination in time and frequency domain can be used to prevent the same time-frequency domain resources from being used by different UEs, thereby reducing interference between UEs. As shown in the right-handed figure on the slide, UE1 is scheduled in cell 1, and cell 1 forwards information about RB allocation to UE1 to cell 2. As shown in the right-handed figure on the slide, UE1 is scheduled in cell 1, and cell 1 forwards the information about RBs allocated to UE1 to cell 2. When the solution of interference coordination in the time and frequency domain takes effect, cell 2 does not allocate UE1 specific RBs to UE2. In this way, the interference performance and spectral efficiency of CEUs are improved.